In this video we're going to go over finding the intersections of polar graphs. So here we've got two polar graphs, one r equals 1 minus 2 sine theta. This is the limicon that we saw in the previous video. And we have radius equals 1, which is just a circle of radius 1 centered at the origin. And down here we see the graphs of the circle and the limicon. And what we can see when we inspect the graphs is that we have 1, 2, 3 apparent places where the graphs intersect. And this first place looks like this corresponds to theta equals 0 degrees, and it looks like if we rotate through to pi, I should say radians, 0 radians. If we rotate through to pi radians, it looks like we have an intersection at pi radians. And then if we rotate through to 3 pi over 2 radians, it looks like we get an intersection of the two graphs. So one way to find intersections is to use the technique of substitution. We see that if we have radius equals 1 minus 2 sine theta and radius equals 1, we should be able to substitute the radius here with 1 and set 1 equal to 1 minus 2 sine theta to find the intersections. So what we're going to see is that an issue arises. So if we do 1, I'll do the right hand side. We do 1 minus 2 sine theta equals, and then by substitution replace the radius with 1, and then we solve. We subtract 1 from both sides, we get negative 2 times the sine of theta equals 0. Then divide both sides by negative 2, we get sine of theta equals 0, and then we take the sine inverse of both sides, we get theta equals, and we get the sine inverse of 0, and we could put the plus 2 pi k to indicate that it repeats infinitely many times. We also want to remember that we get two solutions when we're working with the sine inverse. We get the angle the sine inverse gives us, and we get the supplement of that angle as well. So we get a second solution, theta equals pi minus the sine inverse of 0, and it's going to be just pi, and the sine inverse of 0 is just 0. So we really get theta equaling 0 and pi, and then those repeat every two, the coterminal angles repeat every 2 pi radians. So we could put plus 2 pi to finish this off, but we don't really need to for our purposes. The idea here is that substitution appears to have found this intersection. This is 0 radians, and it appears to have found the intersection at pi radians, and the solution process using substitution has seemed to fail to find this intersection. And what we want to do is identify why sometimes we are unable to find an intersection using this technique, and we'll do it by taking a look at the GeoGebra file that we have that goes with this. Hopefully it doesn't take too long to load. There we go. So here's the graph showing the intersections of the limicon 1 minus 2 sine theta with the circle. And what we want to see is what's going on here. When theta equals 0, we're in this position right here where 1 minus 2 times the sine of theta is going to equal 1. And a circle is going to be located at 0 degrees, is going to be located here as well. So at theta equals 0, we have the intersection of the two showing up. As we let theta vary, so as I rotate around the circle, what we want to notice is that the point L on the limicon and the point A on the circle, when we get to that pi over 2 position, A is at a radius of 1, and L is actually down here with the being reflected through the origin with the radius of negative 1. So it's at pi over 2 negative 1. So they're opposite of each other at that point. And as we continue to rotate through, when we get back to theta equaling pi radians, the points on the circle and the limicon are together there. As we continue to rotate around, when the point A on the circle gets into the 3 pi over 2 location, we see here that the point on the limicon is in that radius of 3 position when we get to an angle of 3 pi over 2 radians. So the reason we're not finding this other intersection is that even though the curves, when we draw them, intersect, the points on the curves as they move, remember, we've parameterize these curves to graph them in GeoGebra. Well, we're at those points of intersection at different angles of theta. So we only going to find an intersection when not only is the radius the same, but the angle generating the radius is the same. And that never happens at this point right here. The angle generating the radius of 1 in this position is different for the limicon than it is for the circle, and substitution won't find that point of intersection.